Hello, junior high, or I guess eighth graders only. Here's the thing. This is one of my lessons that I really enjoy. Reason for it is it's pretty obvious what it's used for. If you're going into a business field where you're going to be working with compound interest, this is basically what compound interest is. It is also, if you're going to be a scientist and look at how organisms are doing or have done in the past, have they increased population over the years or are they decreasing, and kind of at what rate. So this one, it's pretty easy to know what's going to be used. Um, The objective is to calculate the results of growth and decay by repeatedly multiplying by the growth or decay rate. When thinking about that, we've kind of already done this when we've worked with geometric sequences, like when I had 2, 4, 8, 16, 32, and so on. You're just multiplying by 2. So we've done this in a way. So I wouldn't be too stressed out. It's not too bad. Sometimes they just hide things with different names. Right now, what I'm trying to do is look up the rule of 72. The rule of 72, the rule of 70, and the rule of 60. What is the rule of 72? The rule of 72 is a quick, useful formula that is popularly used to estimate the number of years required to double the investment at a given annual rate. So, double or years to double equals 72 times interest rate, where interest rate is equal to the rate of return in the investment. Oh, and they got some fun things there. Just thought I'd do a little backup deal on it because it says use the rule of 72 to find the time it would take for a population to double. So obviously we're going to figure that out today. Example 1 is the population of a county has grown 2% per year for the last 5 years. If the population is now 1,200,000, what will the population be in 3 years at the current growing rate? Using the rule of 72, about how many years will it take for the country, it is country. I put county earlier. We're going to go with county. Probably should be country when you're working with 1.2 million. But maybe we will go country for that reason. Okay. Population to double at this rate. Well, just gotta think of a couple things here. Obviously, we're going up with 2% per year. To do this, so you'd have to just go and calculate it out. Well, the next year, if it grows 2%, I am looking at the fact that I already have 1,200,000, okay? And I'm still going to have those people. So I'm going to have 100% of those people plus 2%. Well, isn't that times 102? The reason for 102 is I'm going to have one whole group and then another 2 of that. So I change that into a decimal instead of a percentage. So after year 1, I would multiply this together and I would get about first year equals 1,224,000 people. That's going to be your first year. Second year, you're going to bring in that number we just had last year. And you're going to take that times 1.02 and find out what that gets you. Times 1.02. And you should get about 1,248.4 or 480 people. That is going to be your second year. That is going to come down here so we can find our third year. And there is formulas that would actually do this for you and keep persistent. But we learned about arithmetic sequences. That's kind of what we're working with right here, as you can tell. We're plugging in our last to use it again. So we've already kind of done this. Probably not on a large scale like this, but we have done it. So you should end up with 1,273,450 because you'd round up. It would technically be 0.6, I guess, if you want to leave it that way, but I would round up. It's a person. Okay, now that got us that. Now, we need to find out how long it will take us to double our population, which goes back to that rule of 72. The rule of 72, and we'll put that right here, 72, is going to be what your population was after the 3 years. So we want this number. And we want to take that divided by 72. Okay. And then after we divide it by 70, well, how does that work? After 3 years, I'm trying to make sure I describe this rule of 72 before you. It's been a while since I've ever actually used the rule of 72. Describing the rule of 72 in your own words. We can divide 72 by an exponential growth rate to find the approximate doubling time at this. Okay, so that's what it was. Okay, 72 divided by, so what you're going to do for growth rate is always 72 divided by percent growth or decay. In this case, it was 2%, so we divided by 2, which then gets us 36 years. Okay? And I didn't leave myself much room for this last problem, and I have a lot to do here. Carbon-14 is a radioactive isotope that occurs in nature. It is used to date materials containing carbon, such as the ones living in plants and animals. Carbon-14 has a half-life of about 5,730 years. If a bone is found, about 1/4 the amount of carbon as the modern day. About how old is the bone? So this is going back into your science of using it. So we're trying to decide if it's A, B, or C. So, reading through the skin, carbon-14 is a radioactive isotope occurring in nature. It is used to date materials containing carbon, such as once living plants and animals. Carbon-14 has a half-life of about 5,730. if a bone is containing about 1/4 the amount of carbon. So, half-life would have gave us right there. Okay? A quarter of life would be a half times a half. We know that, which equals 1/4. So we'd take 5,730 and 5,730. You're going to get 64, 1. So you should get about 11,000 years. Give or take, we're a little above that, but that's the closest one, so we're going to go with A. Do you guys understand that? Obviously, if you have questions on that, ask me. Basically, like I said, you have 1/2, well, that's 5,730 years. But you want 1/4. Well, to get 1/4, you'd have a half of it. And then, if you want another that many years, you're going to have a fourth of it, which then is going to get you 5,730 years. Cool thing about this is if you're interested in finding out how old things are, this is kind of how they do it. Maybe you don't enjoy that, but it is kind of interesting, to say the very least. Okay, find the next term in the growth sequence. What is the constant ratio? Well, I would say right now, I'm trying to think what my common ratio would be. First one, you're going up by 8 if you're adding. 8, 12. That one is quite a bit of a jump, I think. So you're multiplying by a percent with no doubt in my mind here. So let's think. You gotta multiply by something. So actually, you know what I'm gonna do? And it's a good way to figure it out when you're working with something. Take 54 divided by excuse me, 36, and you should get 1.5. Take this divided by each other, and you should get 1.5. This and this, you should get 1.5. So what's taking place is if you go the other way, we're multiplying by 1.5. Multiplying by 1.5. So our common ratio, or constant ratio, is 1.5. Okay? Or multiplying by 1.5. The other thing is find the next term. Well, now we know it's 1.5, so 54 times 1.5, 81 would be our next number. Okay. Okay, set D. The number of bacteria in a culture increases from about 2,000 to about 4,000 in 1 hour. Assuming the bacteria population grows exponentially, how much longer will it take the number to increase to 16,000? You can do this a couple different ways. This one's not super duper hard, and there's probably a better way to do it than just sit down and figure it out. Right now you went from 2,000 to 4,000, which means it was a rate of 2 multiplying by 2, and that was first year. Okay, second year, then if we're going to multiply by 2 again, or first hour, I guess. My bad. Hour. Second hour. And then it would be multiplied by 2, so in 3 hours. So I would say this one is 3 hours. How much longer though? So it would take 3 hours, but we're already at this, so you'd be 1, 2, 2 hours. Now once again, reading your directions or your problem is key. There is your homework. Shouldn't be anything too extreme. Give it a shot, see what happens.